Recording has started. This is
Thank you,
March
sir.
25th. March 25th, the Western Automation 7 a.m. technical class, and today's host is Chad Christopher.
Good morning, everyone. So Pierce asked me today to give a little overview of the state of the art, for lack of a better term, of laser sensing from the broad term in our space. It's come a very long way over the years, and it does afford us a lot of ways of solving problems that were quite difficult in years past. So we're going to kind of hop through what it actually is, whether or not you can put them on a shark, and you can use these things for lots of different applications. So jumping right into it, what is the laser? And I'm sure, Pierce, you probably have a nice long story about, was it actually the Alan Parsons project that was the genesis of lasers? I don't remember, but there's some jokes in there too. So laser technology. Laser is a measurement value recorder that works using laser technology. This is a little verbose, but we got to start somewhere. So the laser is a sensor converting physical measured value into an analog electrical signal internally. The laser sensor uses laser light rays to sense an object. We talk about laser sensors as transducers. Lasers convert light energy into electrical energy. Laser sensor is used for contactless measurement in its kind of most basic form in our space. In terms of, what really is a laser, it's an acronym for light amplification by simulated emission of radiation. That's a lot of words. Effectively, it's a coherent light beam where all the light waves are traveling in the same orientation. It allows for a lot of photo energy concentrated into a small space. As you can imagine from higher end lasers, or I should rephrase that, higher powered lasers, you can get into cutting metals, theoretically downing enemy aircraft, all kinds of stuff if you got enough power to basically make the system operational. And the final line here, the laser sensor generates energy in the form of light, which is close to the optical portion of the electromagnetic spectrum. That's just a long way of saying all the lasers basically are in the lower bandwidths, in the visible spectrum, not all, but most that are used in our space. And they use a very small notch of bandwidth. So like a red laser is probably operating somewhere at like 660 nanometers, plus or minus a few, versus your traditional LEDs, even though those have gotten much tighter, would have a much wider emission scale and pattern. And as always, if there's any questions as we go through here, please, by all means, jump in and shoot them out. So I swear there'll be less text coming up here. Working on a laser sensor. The laser beam is incident on the object which is to be sensed, which is effectively, in most applications, we're going to shoot that beam perpendicular right to the surface of what we're looking for. We have a very large amount of light energy, so it's going to appear as a very small, very bright dot on the surface. When the laser beam is incident on the object which is to be sent, some part of the light will be reflected back by the object. This reflected light is sensed by a receiver in the sensor. Oops. And that gets us, to a photodiode or a presence sensing array, something to that effect. And then the signal internally is basically converting either how much light energy is coming back or where it is landing on the receiving element to calculate the signal strength coming back or the position of an end device. And we'll look at that a little bit more in a minute. The laser sensors are typically very fast. They have a high amount of processing power in them. And of course, the speed is fixed going out. So that affords us a secondary way of doing longer range detection, which is called time of flight. And we'll talk about both of those. So the general areas where lasers are deployed in the automation space, kind of run down this list. The simplest being a laser projector. However, this can be quite useful in a lot of applications. So in the case of a laser projector, you may have a very simple photoelectric sized body, something to that effect, with instead of a normal internal emitter receiver or an opposed pair, something like that, where we're literally just sending out a laser line for feedback for an operator. They could be using it to position materials on a machine, for a QC check, a surface, visual surface check by using a higher performance laser line generator. Let's see here. I'll get to them. So like in our QS18 family, this is a very low cost photoelectric family, but we have in this family a series of simple laser generators, either a small spot, a circle. So there's applications for that to be able to see that somebody's hitting the right spot or using it as a fiducial for alignment. Vertical line and horizontal lines, which are just in line with the main axes on the sensor body, and then a physical cross point. And a class 1 or a class 2, just basically how bright it's going to show up. Now, we can also utilize these with any photoelectric receiver, and we're showing a smattering of them here, which allows us at 50 feet of distance to have a very high amount of excess gain. Excess gain is the amount of signal above 1 required to change the state of the receiver element. So you can see like here with this Q23, it's basically saying at 50 feet, if I use this laser emitter, I still have 7,500 times the required amount of light energy to turn the sensor on and off. If I go to the class 2 version, I'm at 12,200. So very, very significant, where if I'm using just the standard photoelectric emitter here, that might be 100 or 200. So significantly lower power. But that ability to do the guidance in applications where you might be just wanting to have a simple indicator for an operator that the part's aligned, or there's some other feature that this brings their attention to. And you can see here, like at just over 1 foot on the circle version, the diameter of the circle is here, but it grows significantly as we go. And that's just a function of the lensing on the system. We also do very high performance structured light laser line generators where the uniformity is extremely high. These are typically deployed in a machine vision type application, but just a different type of device on the same spectrum of product. And we actually have some control capability over this over communications versus the other ones. But I don't know if you caught the pricing on those ones we were just looking at. Those are about $100, and this thing is $1,250. So it gives you a little different idea there on performance level. So jumping back here, kind of talked on the laser photoelectric sensors. Generally, what that boils down to is either your laser opposed sensors, where we're using the laser to have a high amount of excess gain, and a very small spot size, which allows for smaller product detection over different or longer distances. That's the lesser use case for these. What we are able to do is really more in the laser displacement sensors, which we'll get to in just a second here. But so yeah, the photoelectrics are pretty simple. They're generally on off, and not going to be giving you really a whole lot of other feedback, just a more precise beam that allows you to have it over a longer distance. It typically makes it easier to align because of the the visible nature of the laser. Laser edge detection is kind of a web guiding type application. You see this in both an LED and a laser version of this. Let's see here. I'm going to jump over to one of our friends in a different space because they make things that we don't do. Micro Epsilon is probably the top product line in terms of the very high-end capability and edge detection and optical precision micrometer. This type of a product allows for very precise measurements of the items involved, or if you're doing positioning of some sort of object coming in and out of this space, very, very high accuracy. Again, we're in the micron level accuracies with these types of devices. Several other vendors out there make them in as well. Banner does not offer one, nor does any other line that we represent, but it's a fairly specific application where you're using this type of product as well. All right. So jumping into kind of triangulation and the features of what is your general deployed laser sensor in the automation space now, which is a proximity or diffuse style where the laser is shot out and hits the target and reflects back, and then we're gathering data off of what's coming back there at that point. So one of the first things we have, again, is because of the laser being very powerful, even the lower class 1 type lasers, which a lot of the sensors are, that is a FDA rating for basically eye safety and emission safety. Class 1 is effectively the lowest, meaning there's really no requirements other than a sticker. Class 2, a little bit more powerful, really still not any particular safety requirement. If I remember the old standard for that, it was someone would have to basically keep their eye perfectly aligned with the laser without blinking or moving involuntarily for something like 1,000 seconds to begin to cause any sort of damage. So fairly unlikely. What's interesting, for the longest time, your pocket laser pointers that used to be used all the time were generally class 3. So they were more dangerous than the photoelectric and laser measurement sensors in the automation space. And then you get up into the class 4 range where now you're talking high wattage, metal cutting, laser etching of materials, things of that nature, where way outside of anything that we're. And one of the things that's interesting with these products now is it's because the sophistication level is high enough with the processing power internally that they will throttle or increase their emission and internal gain to try to optimize to see the targets you're telling it to see. Whereas older sensors, pretty much one size fits all. If you have too much power to see a shiny metal object, you maybe are trying to angle the sensor or maybe put a polarizing filter in there. When if there's a dark target, you may not have enough energy to see it at all. So you're trying to get closer, and worst case scenarios, if you have to be able to detect both types of targets in the same space, that becomes quite challenging with older technology. One thing we do offer, or I should say the industry offers with laser, is it is focused. However, it doesn't always have to be. There are some bigger beam sizes depending on what we're needing to do, and they allow for some surface averaging depending on what you're doing in your application. So typically you're going to have a small space, which means your averaging space is smaller if you're doing any sort of color detection or you're worried about color sensitivity. So in the instance here, where we'd actually be using a sensor to determine which color we're looking at, we would want that to be as focused as possible. So as it blends from one to the other, we're not averaging a very large space, whereas here, maybe a traditional LED would be doing that and giving you some trouble. The small beam is good for profiling. So if we are trying to measure a product moving through a space and doing the profiling on it, of course, the smallest point we can get away with is typically going to be your best performance. In products we offer, we have sub 10 thousandths focal point available. And there again, it just depends on the application, how far away you mount it. We have focal distances on the lasers. So if you want that averaging, you mount it specific. You don't want averaging, you mount it at that specific focal point. You do want averaging, you can move it closer, further away, and the beam will get bigger. And that's what we're showing this last position, where sometimes you actually do want to average over a bit. So you're going to optimize for a little bit bigger beam spot to get an average reading off of this versus several very small pinpoint readings that would give you, various types of outputs.
Chad, question. I'm not sure if I heard you correctly. Did you say that if you want a more spread out or dispersed contact with the surface you're monitoring, you move the sensor closer?
Depends on the sensor. There's specific focal points on industrial sensors. Some are adjustable from some vendors, very few. So like in one of our Q4X's, say the nominal focal distance is at 100 millimeters. If you move it closer or further away, that beam is going to grow because you're basically past that peak focal point.
You're talking lasers now or optical sensors in general?
Lasers more so. Optical sensors generally are maybe collimated, but they just expand. They don't get smaller. So let me see. That makes sense?
So the laser has sort of a tight point at some given focal length. I didn't realize that. I thought lasers expanded in a cone.
Yeah, they are pre-focused. Like we take one of our high-end lasers here, like our LM series. You can see here, the resolutions that we're capable of. But if we get into this guy.
And this is a $1,200 device that you're showing us now.
Yeah, give or take. Yeah, the performance levels of these devices, are significantly higher than they used to be, and the cost point has come down significantly as well. So let's see here. I know here we go. That's what I'm looking for. So again, this family, this unit that's kind of max range is 80 millimeters. Our XY beam spot pattern is focused out at the furthest point. So if I'm closer, I get a bigger spot. In the 150 millimeter version, my focus is, it's also a distance on this one. So we're giving you your smallest spot size at kind of the maximum range. Some of the other ones are focused inside their sensing range. So they might be at 50% of the rated range of the sensor. So if you get further away or closer, that beam's going to get a little bit bigger. But does this make sense?
It does, yes. Thank you very much. So the laser itself, the physics of it it'll disperse, but you must have some sort of optics that are creating this focus point.
Correct. Yep. They're actually focusing it internally here, and then you'd be outside the range, but of course you would start to see it immediately start to expand again past this point in space.
Thank you. It's a great explanation. Thank you.
Yeah, and it's it's an important game to play because again, if you're looking for very precise features, like we've we've done testing for chip in pocket or double chip applications with this, where we need to be generally right at the high focal point. Whereas if we were just trying to see a surface measurement on a brushed metal, we'd actually want to have some averaging because the features of that surface could really throw up some odd readings. So like if I go back here, where if you had a real focus beam, you would get very specular readings as you moved across here, where if we're averaging over this, we'll give you a much more smooth readout value. So getting into the real way these triangulation sensors actually work versus your just traditional discrete photoelectric or laser sensor for that matter. What we have in these types of products now, depending on how old they are, is what used to be called a PSD, a presence sensing device, which was like a linear array of basically photodiodes with a certain resolution that, depending on where the light hit, we would get a different A to D conversion and be able to tell with pretty good accuracy out here what we're looking at in terms of a switch point. What you also see is now a lot of these types of sensors are actually deploying CMOS or CCD imagers, mostly CMOS because they're less expensive. But now we're getting 2D positional information coming back. So it allows us to interrogate for how far away it is, plus laser light intensity, which gives us a whole additional level of capability in terms of looking for all kinds of things, one of which you would have never considered to try to do a clear object detection with a laser in the past. But now, because of the ability for us to check distance and light intensity, or maybe light characteristic is a better word, we can do clear object detection with kind of, in Banner's case, any sensor that has a setting we call dual allows us to do that. It also gives us the ability to do very challenging position detection using that technology as well, where we're again measuring both the angle coming in and very specific information about how that image of the laser being hit back onto the receiving element looks, how big it is, where the position is, what the standard deviation is. That gives us really, really good capabilities for difficult detection. And what you end up looking for then is, in this type of application, is what we call a key feature then being is minimum object separation. And this is how far apart your target and your background can be for us to actually be able to tell what it is, if it's the thing we're looking for or if it's the background. This is very key in triangulation-based sensors. But there again, if we deploy our dual mode setting, it gives us some more capability. But anyway, this is a pretty typical application. Minimum distance a target must be from the background to be reliably detected by a sensor. An MOS of 5 millimeters means that the sensor can detect an object that is at least 5 millimeters from its background. The triangulation sensor and time of flight, which we haven't talked about yet, we'll get back to that. Triangulation technology is more robust in the near range, while time of flight is more consistent across the entire range. It appears to be kind of in the industry where you go from triangulation to time of flight is about 1 meter of sensing distance. And that's really a function of, if we're trying to do triangulation and we want to measure a long ways, I have to get the laser and the receiving element further apart. So I can actually get a usable angular measurement out of it. Most of the sensors just don't want to be that big to go into triangulation at longer distances. So that's where we can start hitting on time of flight, which we'll look at more in a moment here. But here is a fairly common series of different type of sensors and what that minimum separation target would be. So these all have reasonably long range. This one cuts off at 1.5. These are probably mostly actually time of flight lasers, but as you can see in that shorter range with time of flight, we're still looking at a standoff from the sensor or from the target to the background of maybe 10 millimeters, maybe 20. Inside of that, like on a Q4 type product, very standard 300. Okay, access gain spot. So that minimum separation distance again we're talking about. So depending on where I am and how far away, sensing wise, you can see on shorter range triangulation products that we actually can still have a very high performance. So in a 300 millimeter version sensor, I can have a minimum separation of about 1 millimeter out almost to 3 inches. And that's just using that standard setting. So really high capability in these types of lower range, higher performance triangulation sensors. All right. So we just mentioned time of flight, which is fairly self-evident with the description. A time of flight sensor fires that laser out and actually measures the amount of time it takes for that reflected beam to come back. These allow you to do much longer ranges. Our standard offering, we do up to a 24 meter in this. And over that 24 meters, you're going to be able to pull a few millimeters of accuracy over the whole range. So very, very high performance type item. So longer range robotic guidance, just sizing, even simple stuff like feedstock for a machine where you're wanting to be able to measure, say, a roll diameter, but you don't want to have it right on top of the roll. You can have this thing 6, 8, 10 feet back measuring it, and now it's not interfering with loading and unloading of replacement materials. So that said, plus now we've actually released this in a very small family, which gives us a 3 meter time of flight in something about the size, well, about half the size of a AA battery. I'm a Q2X family. So lots of really good performance in these types of products as well. And a key thing, here again, we'd mentioned earlier is that excess gain. So how much punch do we have at distance to be able to see targets in that time of flight type sensor? They are capable of reading very bad targets. I actually have an application where I use them to profile a conveyor full of garbage. I have an array of them, and they're using it to give you a rough profiling from about 12 feet in the air of what the stack looks like coming in. So now what's evolved out of single beam time of flight is 3D time of flight. This is a really interesting technology. You're starting to see several vendors make this. Banner's got a unit in play now called the ZMX, but the capability of this type of sensor is extremely useful. And what is happening now is you're sending out a two-dimensional beam grid of infrared lasers. The resolution on this is about 250 pixels by 250 pixels. So it's not a vision system. It's really designed for profiling the space. And what you get into is the ability to do container fills and things of that nature. We can also use it for detecting a high point in space. So we're scanning one application where we're just looking to see where the highest point in the kind of the cone space is relative to the front of the sensor. And we can output that information over Ethernet to either do a collision avoidance, or you could do a pick type applications. So we're showing a couple other interesting things here, which would be for robotic guidance. In this application, we're able to tell the system, okay, I've got 3 boxes here, so I've got these 5 open spaces to put your box, because what we're doing is, proper stacking. Another application for this type of thing is basically bin filling for shipping applications or transport applications. It's very expensive to ship air. And so being able to use a sensor like this allows you to make sure this fill is adequate for what you're trying to do. If you look at our friends at Micro Epsilon, their surface control series is a very, very high performance measurement type device using this basically the same type of technology. So a 3-dimensional time of flight point cloud laser system. These are in the right applications. Yeah, these are fantastic products. It's way outside of anything we've got in our toolbox, but at least be aware of, this type of product exists out there. There's several manufacturers, both kind of more vision based and more laser based. It just really depends on the application. You can see here where they've got 2D laser scanners plus more optic based systems. So yeah, that's kind of the top end of the state of the art for doing these types of things. You have longer range profiling type devices, which would be like LiDAR. And it gives you the ability to scan a bigger space. This type of technology now is extremely powerful. They're utilizing it from satellite-based systems to scan, ground locations. And what's interesting is when you start seeing stuff that they can find, scanning from space using LiDAR imaging systems is all kinds of crazy stuff that you'd have never found otherwise. So what we're starting to see is by doing these infrared scanning systems from the satellite base, they're able to go back in and profile things that have been hidden under forest canopy, all kinds of interesting stuff. So we do not play in this space. It's just very cool. And it's really the kind of the penultimate solution for anything in kind of the laser space right now.
Chad, what does LiDAR stand for?
Let's see here. I can't remember. Light direction and ranging. Laser imaging detection and ranging.
And so if it's light, how does it penetrate through a forest canopy?
Magic. No, I I think it's got a lot to do with the frequency ranges this is operating in. I don't know if these are at more, where are we at here? Wavelengths varies with the target. So infrared, ultraviolet, backscattering. So yeah, these are going to be functioning well outside the visible spectrum typically, especially for satellite-based stuff. But I imagine they also probably are starting to have technology like this in the much higher wavelength stuff, approaching X-ray and stuff like that. So yeah, if you want to go down an interesting rabbit hole, start looking up all the LiDAR profiling they're doing on Earth. This technology, though, in terms of industrial, has been around for quite a while, where you see either a safety application or a profiling application. And our competitor here doesn't want to cooperate. So you'd have these rotary scanning laser devices for typically machine safety, but then also vehicle profiling, space profiling, large package profiling. That's where this kind of tech lives in the automation world. It's kind of the gap between typical radar sensors and purely optical laser sensors. A lot of these are going to be infrared lasers. So that tech is out there as well. But going back to kind of the home team here, let me find the document I'm looking for. We do have a very nice little laser solution brochure that kind of covers all of our families and what we do. I pulled some of these graphics from here. It's a great little refresher on how this tech works versus typical photoelectrics and things like that, and a little choice tree to walk you down. But what is interesting, we look at all this stuff, but I just like to get to this comparison chart. So our families of items is principle of operation, triangulation, time of flight. So Q4 is all triangulation. We get into the Q5s, we do both triangulation and time of flight. You can see here repeatability is very good on a kind of a standard automation type product on these units, but even here, like a 10-meter time of flight, we're getting 1 to 3 millimeter resolution. This new Q2X, which is the little small one I was telling you about, 3 meters of range, 1 to 3 millimeter resolution over that space for, I think this thing lists for it's under $200. So gives you some really interesting measurement capabilities. And a lot of these types of products would have analog outputs and things like that over the years, which they still offer, but now everything is going to be industrial network. So it's either going to be IO-Link or Ethernet natively. And you're just going to see that continue no matter what it is. Even the little Q2X here is an IO-Link based device. The LTF, so this is the laser time of flight, 24 meter. Depending on where you are in that sensing range, we have better than 1 millimeter of resolution. And so just how the families roll, kind of round out here all the way back to our really high performance laser measurement, the 80 and the 150. So you can see here, our resolution is very high on these units because this is in millimeters. So a nice little document here, kind of covering all of our various solutions, how things work, options, other things we can do here, and keeps it pretty simple for you. But yeah, the whole space has really evolved in my time in the sensor world. The cost used to be very high. The options weren't very good. The resolutions weren't particularly great. Way back in the day, like a Keyence LK measurement system was something like 30 grand. We can do the same type of resolutions now. That was, back then. We can do the same resolution measurement now for $1,500. So the ROI on deploying these types of systems is much better than it used to be. Any questions?
So is this taking away the top of the traditional optical sensor market in terms of applications?
It really is, yeah. What you're finding more and more with just LED-based photoelectrics is they're the very, very inexpensive solution. Hey, I got to see this big cardboard box on a conveyor, and I want to spend $25 to do it. That's where those have really been optimized into. The only caveat to that is where you have color measurement, things like that, where we can do with white structured lighting and RGB value measurement. But yeah, for the most part, I can speak from my experience. Any application I'm looking at, my default starting position is a Q4X. It's got a myriad of settings and times and other things that we can do inside of it. So it's kind of that, if I throw that at a product or problem, it's very likely to solve it, unless there's a very significant cost problem, which, okay, then we maybe go into one of these other spaces. But yeah, for the most part, any difficult sensing application, we're going to start in this space.
I have a more general question. If I have a really difficult sensing application due to dirt, water, what have you, and I have a high reliability requirement, in general with sensors, and understand I'm a neophyte at sensors, but in general with sensors, does it make sense to use two different technologies and have some redundancy? Have you ever done that in terms of a philosophy of solving an application?
We have. It doesn't come up that often, but you may have an instance where you'd even just use two of the same sensor. There are some sensors with SIL ratings on them. That isn't really solving what you're talking about, but that's, from a longevity of the device standpoint. Yeah, I mean, like a lot of things, it's making sure you get the proper things specified up front. If you have, this is, I guess, kind of a back to the basics on lasers. A lot of folks think the lasers will burn through things and see through things. They will not. A laser hits a water droplet, you no longer have a laser. You have a diffused LED spraying all over the place. So we do want to make sure we're picking the right technology for the job. And I think like a lot of our products, if it's specified properly, that's a very small likelihood of being an issue. But you certainly could do either redundancies or multiple technologies if you're in that very, very high reliability state.
Do you mind if I throw a specific application at you, Chad? Not to put you on the spot, but you're our resident expert, and I ran across a sensor application the other day where we're sensing the edge of a cutting wheel it's in a cutoff machine, high cycling cutoff machine. So cutting fluid, the abrasive dust coming off the wheel as it wears. And the customer was having a nightmarish time because the original Swiss manufacturer was using a piece of what looked to me like aquarium tubing that was up against the side of the wheel, and it was sensing pneumatic back pressure.
Oh.
And I was wondering what technology you might recommend to either back this pneumatic sensor up or replace it.
Were they just trying to detect if it had hit in a certain spot in space, or
wheel wear?
Some sort
Once the pressure is gone, it means the wheel is not up against, is not resisting the air coming out of the sensor or of the tube, and therefore the sensor, the pressure sensor on the other end of the tube, senses a drop in pressure, which means the wheel needs to be replaced.
Sure, yeah, and that's a pretty good instance for kind of doing a redundancy. I'd probably look at having a very robust proximity sensor where it would be able to have a pretty tight cutoff in space. Of course, it would have to be close to the wheel when it goes into whatever position it's going into. But as that wheel weared, it would eventually no longer be detected by the proximity sensor. And you could stagger a couple of them, kind of an A-B type scenario. That coupled with the pressure, back pressure on the wheel is probably about as good a detection as you're going to do, because that is a terrible environment. That stuff will get stuck all over everything. The cutting
Eh,
oils and the grit that gets in there.
Yeah, it's a fine paste that eventually starts to build a surface on everything. So a prox sensor, does the wheel material have any effect on the selection of the prox sensor?
It does. I'm assuming it's metallic of some sort. If it's purely a grit based system where there's no real metal content to it, then that wouldn't work. And we'd probably have to look at something else, like a extremely high powered optical pair that will be able to see through a lot of crap for a long period of time, eventually needing some maintenance, but they'd be able to see through a lot of dirt and grit and grime for a long time. And kind of the same thing, you get that switch point in space where when the wheel comes back, it can check, and it should always be breaking the beam. And if it isn't, it's no longer, it's shrunk enough that it's not functional. But
Okay.
that environment, of course, would be actually a pretty bad application for a laser type sensor, unless it was something we could put further enough away that wouldn't get into wouldn't get contamination on the lens, which could be. I mean, that is the beauty of some of these units where, we could have a time of flight unit, something like this, where I could theoretically be 10 feet away from the grind wheel and shoot that laser beam at it and measure that position to, maybe 1 millimeter accuracy.
If I were to put a tube on the end of that LTF-12, say 2-inch tube, to prevent a lot of the grit and grime from getting into it, and shape the tube such that the grit couldn't block the end of the tube, would that allow the LTF-12 to function within, say, 2 inches?
No, totally different type of product. You'd have to look at like the LM type 80 product, but if you could prevent the grit and grime from getting into the lens area, which is probably very difficult or impossible, that would theoretically work, but I suspect that is not realistic. We
Okay.
could
All right.
certainly talk more about it offline, but you being further away from it would be better at that point. Or, like I said, going to just a through beam type device that can really handle a lot of nasty type grit, things of that nature. The other thing would be is we actually do have opposed ultrasonics that are fairly immune to a lot of that type of stuff.
Wow.
So
Yes.
you could theoretically shoot an ultrasonic beam across there and maybe be able to get your reading. Just actually pulled these for another customer right now, but these guys are stainless steel IP69K, smooth, hygienic design, but they're also good for these types of awful applications. So we have an ultrasonic wave across there that you'd position in such a way that when the grind wheels ground down enough, it would allow this beam to be made.
Cool is that? And what are the cost? What's the cost range of those?
This pair is about $1,500.
Okay. Excellent. Well, thank you. Appreciate that. I'm going to call Todd Price into this situation, but I just wanted to get an idea.
Cool. Any other questions? All right. We'll actually turn you guys loose a little bit early. I'll put my favorite picture from the show back up.
Well, thanks, Chad. I appreciate that. I learned a lot. Next week, we will be off for the holiday. And the following Monday, we will have a class on VFD types and the applications that they're intended for. So an applications-oriented variable speed, variable frequency drive subject matter. Chad, I need to talk to you after the class regarding uploading the recordings. I think I've almost figured that out. And for the rest of you, it's 7:54. Time to go to work, and we'll see you in 2 weeks. Have a nice holiday.
Thanks, Pierce.
Thank you, Pierce and Chad.
Have a great week.
Hey, Chad, it's Joe. How you doing?
Good, Joe. How you doing?
Good. Hey, I had a quick question on the profiling sensor. Is that constantly profiling, or is there a refresh rate? So, for the
Yes.
illustration where you had the robot, is it where it's stacking, it'll ignore, or you can delay the
You could trigger it.
Mhm.
The actual scanning rate on this is, don't put in here. Bear with me a second. It isn't. It's closer to a vision system in response speed, so it's like 100 milliseconds.
Oh, okay, yeah. So it's
because it's
pretty
actually
much
going out and checking everything. It isn't just streaming data real time. This is an Ethernet based version too. We've got
Mhm.
one coming out here pretty quick. That's going to be, I think it's going to be like 70 by 70 pixels and IO link in that K50 radar package. That's going to be out pretty quick for even kind of more simple applications. But
Cool.
let's see, what do we show here?
Typically, as it's stacking, right? If it's kind of, let's just say it's kind of constantly profiling, it's gonna, you can delay when you want to take the measurements. In other words, when the robot's out of the way, for example.
Yeah. So like the free
Okay.
run, if you just put it
Yeah.
in a free run and let it rip, 150 milliseconds is its updating rate. But if you
Right.
do over here in the Ethernet stack,
Yeah.
trigger.
Yeah, because similar to the bin loading application, they're not always going to fall perfectly, right? You may have some voids and gaps. So, there may be cases where someone would want to go in there and rearrange it so you can get a couple more boxes in there, let's say.
For
So I
sure.
could see that happening. Okay, cool.
Yeah. It you can trigger it. I mean, it could be because it's completely communication controlled. It's nice. You can actually change the whole field of view on the fly. We're doing this in an application, which is pretty cool, where we're looking at the side space for the highest point, and then we're
Yeah.
also going to check. Then we change the field of view over Ethernet to go look to see if there's a very specific feature sitting out proud over here. So
Okay.
we just toggle them back and forth over Ethernet, and that whole scan probably takes 1 second.
Yeah,
But
that's not bad. And
it's
those type of applications, that's perfect
yeah.
for the most
Yeah,
part.
you're basically getting all that information here, but yeah, your ability, this is the inbound stuff, so you can change all these set points on the fly
Cool.
and trigger it. Yeah, it's a really cool little product. Not a million
Yeah, let me know when
applications for
you're
it,
up
but
north again. We need to catch up, grab some lunch.
yeah, absolutely. I keep meaning to get Temecula, and everybody keeps raining on my parade.
Yeah, I was down there last week, and anyway, I'll talk to you offline on it. And yeah, we'll catch up. Thanks, Chad. Have a good one. Have a great
All right,
week.
sounds good.
See ya. Bye.
Thanks, Joe. See ya.